Well, today I want to talk to you about Unit 6. We begin a brand new unit. It is Unit 6 in chemistry, and this is podcast 6.1. In this unit, we're going to be talking about the states of matter and thermochemistry. So let's get at it. Mr. Sams is not here today because he's very busy. He's actually in building, but he might be joining us later. We will see as we go. Okay, hey, podcast 6.1. We're talking about KMT. KMT, what the heck is that? Well, I'll tell you about that in a little bit. And pressure. Hey, KMT, there it is. It's called the kinetic molecular theory. Now, what do I mean by the kinetic molecular theory? Well, kinetic has to do with motion, so it has to do with kinetic energy. All right, so if we think about this, kinetic means motion. So, for example, if you were to look at, say, somebody who's an amazing athlete, I don't know, pick your most amazing athlete that you think is amazing. You know, I like to ride bikes, and Lance Armstrong was the best biker in the world. He was kinesthetically gifted. He's gifted in the art of moving. All right, and then you think of the word molecular, it comes from the word molecule. Molecules, of course, are the small particles that we talk about, and then theory. So it's really kind of the moving molecule theory is really what this kind of gets at. So we will learn about kinetic energy today. Okay, hey, it's the energy of motion. As things move, they have energy, and there's actually an equation for the energy of motion. Kinetic energy is equal to 1/2 times the mass of the object times the velocity squared, where mass is measured in kilograms and velocity is measured in meters per second. There's also another equation we'll learn that. It's also 3/2 times R times T, where R is a constant and T is the Kelvin temperature. And we'll kind of get into that a little bit later. Okay, there are 3 tenets to the theory, the kinetic molecular theory. It says that gases are small, hard spheres. So there are many, many tiny, hard spheres that are moving around in space and such. Okay? So I want you to think of molecules as these tiny little spheres that I have, and they're moving around. And so, well, they move, yeah. Okay, and they move in constant motion. So sometimes they're going this way and then that away, and so they move around. So this sphere might move in this direction. This is the sphere, and then another one might be moving in that direction, and another one this way. And it's 3-dimensional. It's not just a flat piece of paper. They're moving in 3 dimensions. And lastly, they are all elastic. Now, what does that mean? Well, you probably heard the word elastic. Things that stretch. Like you got elastic in your pants or something like that. Some people have that because they weigh too much. Okay, yeah, Mr. Sams is probably one of, no, that's just a joke. The elastic, and so something that bounce. So when they bounce elastically. Now to a scientist, that actually means they lose no energy in their collisions. Okay, and you kind of see a picture right here. Actually, I should probably erase this, hold on. So this picture kind of helps illustrate that. They're kind of moving in constant random motion. Hey, cool. Here you can see this sort of cool animation. We have several gas molecules moving around, and as they move, you can see them. Well, they're bouncing and they're colliding elastically, not losing any energy when they collide. Okay, so more things about this kinetic molecular theory. Kind of talk today. As you increase the temperature, this makes sense. What happens to the kinetic energy? Now, temperature is a very important thing we're going to talk about, but actually what happens is the kinetic energy goes up, or it increases. That's right, okay. Because you see, temperature really has to do with how fast the molecules move. So one molecule going here, it has a particular temperature, and then another molecule might be going much faster, and of course that would have more energy, okay? So as you increase the temperature, the average velocity of the particles goes up. They both increase, or they, yeah. So that's, as I kind of just talked about there. I think it's going to help to understand. Okay, let's kind of have a conversation about, interesting question. What is the difference between a hot day and a cold day? And a cold day. So here we have a picture of the desert down here, and then we have a big iceberg. Well, really, the difference between a hot day and a cold day is how fast the molecules are moving. So, oops, hold on. So in this picture, the molecules are moving faster than they are here, as illustrated by the longer and the shorter line. So the average speed of the molecules on a hot day and a cold day are going to be vastly different. Now, it's the average speed, so even on a hot day, you'll have some molecules moving slow, and over here you have some molecules moving fast, but the vast majority of them are, at least on the cold day, they're moving slow, and that makes it cold, and then on the hot day, they are moving fast. So, hopefully that makes sense. So that's an important thought to make. Okay, in fact, here is a way we can look at this. We can take a cold gas, and you can see that we have the speed of the molecules. Now, there is actually a misconception a lot of people think is that all the molecules move at the same speed at a given temperature, and that's not correct. It's the average speed. So here are my molecules that move slow, if you will, a short arrow, and then over here I have some molecules that are going uber fast, and here's my average molecule right here of the cold gas. But the average of the hot gas, well, that's about right here, and so he's going pretty fast. And over here, molecule right here, he's going way, way, way fast. But there's not too many. See, his low ones are equivalent to the average of the blue ones there, you see. Okay. Now let's talk about the concept of pressure. All right, what is pressure? So if I take my head and I push on my head, is that, yeah, it's kind of pressure, yeah. That's silly. Okay, what is pressure? But we're not talking about pushing on Mr. Bergman's head. We're talking about pressure of a gas, okay? Now, when we talk about solids, liquids, and gases, if you look at my picture here, think of these little spheres as gas particles flying around. And they're hitting the container. And when they hit the container, well, they bounce and they hit with pressure. So the technical definition of pressure is the force exerted by a gas as it collides with its container. So I want you to kind of take this picture in your head. Think of the ball, and the balls are moving around and hitting, hitting my head. Ooh. Thousands and billions and moles of molecules are hitting me constantly, okay? And they are exerting a force upon my head, okay? So let's talk some more. Now, what the heck is a vacuum? Well, up in space is the absence of gases. A vacuum is where there is no gas. So it is considered a vacuum. So space is a vacuum because it is filled with primarily empty space. Now, if you look at the picture here, I have a picture of a galaxy, a spiral galaxy, and it is, there are gas clouds, which are stars and things in here, but most of space is just empty space. Okay. Interesting thing about pressure, we can actually measure the pressure of our atmosphere upon the Earth. So here's the Earth right here, and we can measure the gravitational force. Now think of all these millions upon billions of gas particles that I'm trying to draw as dots. They're coming more as dashes. But there's all these particles, and they're all moving around, and they're hitting you, and they're hitting me. Well, because of gravity, more gas particles are closer to the surface of the Earth, and less are further up here. And as you get further in space, they're much more spread apart. And eventually you get to kind of, actually space is not a complete vacuum, but you would find very few particles, per cubic meter or something. So the pressure exerted by the gases in the air is called the atmospheric pressure. So if we had a 1 meter column of gas, of air, so this is 1 meter squared, so 1 meter by 1 meter. That's 3 feet by 3 feet. What would be the pressure at the surface? Now at the surface, it sort of depends on your altitude, which we'll talk about. Okay, so the atmospheric pressure and altitude. Let's talk. The higher you go. Now, those of you who live here in Woodland Park and up in the mountains know that we have less air up here. People talk about that. So the higher you go, guess what? The lower the pressure, right? The lower the pressure. So we have lower pressure. So here where we live in Woodland Park at 8,500 feet in elevation, we have about 0.75 atmospheres. Now we'll learn about the units in a little bit. One atmosphere is the pressure at sea level, 0.75 where we live. And if you go to the top of the tallest mountain in the world, what this picture is, it would be even much less than 0.75 atmospheres. And so in fact, here's a graph of that. Okay, air pressure versus the height. And this is in kilometers. So when you go up and higher, if we are at 8,000 feet, 10,000 is 6 miles, what are we at? We're about 10 kilometers up, maybe 12. I don't know, 5,280 feet. No, we're only about a mile, so that's, yeah, well, actually, we could probably figure it out. 0.75, it'd be 750. This is where we live right here, yeah. So we're at about, well, just 1 kilometer. Yeah, that's not too bad. 1 kilometer up. Doesn't make sense. We're more than 1 kilometer. We're about 2 kilometers. Yeah, that's 80. Oh, 0.75. That's 90. 0.75 is here. So yeah. Okay, yeah. Here we are, right here in Woodland Park. Now, if you are at higher elevation, if you could get to 10 kilometers, this is very low pressure, and you couldn't survive. Okay. How do you measure pressure? Well, we measure pressure with a thing called a barometer. It's a device that measures the atmospheric pressure, and this is how it works. What they do, you know what? I should probably show you a short video clip that helps explain this. Yeah. All right, today I want to talk about how a barometer works. A barometer is a substance or a device that measures air pressure. All right, I have a simple barometer. We'll talk about that here with me. I have a graduated cylinder filled with water. Now, to make this more illustrative, I'm going to add some food coloring so we can see this. I'm going to pour some food coloring. It looks like green food coloring. I'm going to mix this up so it's easy to see. All right, so I got some green water. I'm going to add a little water so I can fill it completely up. I don't know if you've ever done this, but it's actually pretty cool. All right, what I'm going to do is going to take this and I'm going to flip it upside down into a vat of water. All right, so I've done that. Now I want you to notice something. Well, I want you to notice that the water goes all the way up to the top. And it's above the level of the water. Now how come that is? Guess what? That is a way we can measure pressure. All right, so as the air pushes down on the water, remember there's molecules hitting the water. Right? They're hitting the water, they're pushing down in the water, and then that pressure from the air pushes this column up. Now, if you were on the top of a really, really high mountain, then there would be less pressure, and possibly you might get a vacuum up here. All right? Now, turns out is if you were to make a column, this column is too short, if you were to make a column greater than 30 feet at sea level, at the very top, you would have a vacuum. Okay? Well, obviously it's not practical to make a 30-foot column of water, but we can use a more dense liquid. So scientists, instead of using water, would do this exact same trick and use mercury, which is 11 or 12 times, something like that, denser than water. And then the column turns out to be about 760 millimeters tall. That's at sea level. Here in Woodland Park, it's like 560. All right? In fact, yeah, let me show you how that works. So here I have an actual mercury barometer. So down here in the bottom of this is the vat of water, so to speak, but it's not water, but it's mercury. All right, and then we can see the mercury column tall and tall and tall, and we keep going and keep going. And we eventually reach this spot right here. And if you look at this spot, the top of the mercury line is about 565, it's just like 56.5 millimeters of mercury. And what's above this, it's empty space, so it's a vacuum. Because mercury is so much denser than is water, then we can, this is how you look at barometers. And the air pressure, all right, if you go back down here, right, think of the air pressure pushing down on this, and which forces the column of mercury up and up and up and up, all the way here in the park, to 56.5 centimeters, or 565 centimeters. Now that changes day to day. This is the pressure that we have today. All right, that was pretty cool. Now that was with water, and of course water is not dense enough, and so scientists use, instead of water, they use mercury, and the mercury can only go up because it's much, much more dense. It goes up to 29 inches or 76 centimeters, and that is as high as it goes. This is at 1 atmosphere. In Woodland Park, it goes to about 500 and something. I think it's 580 on an average day. It changes because it's a weather issue, right? Okay, so how would you actually make a barometer? Well, first of all, you would fill a tube 1 meter long with mercury. You would then put your thumb over it. I wouldn't recommend that because, of course, that would it'd be a problem. Flip it upside down, and it would be completely filled. Okay, no, it wouldn't. It depends on your pressure. What you'd have up here is you'd have a vacuum. And below this would be equal to the height measured in millimeters of mercury. So if you are at sea level, this would be 760 millimeters tall, or 76 centimeters. Now, here in Woodland Park, we get like 580 millimeters because, of course, there's lower pressure at our higher altitude. Okay, how do we do pressure conversions? Okay, well, first of all, 1 atmosphere is equal to 760 millimeters of mercury. Kind of heard me talk about that, haven't you? It's also equal to another unit we haven't gotten into too much detail. It's called a kPa, or a kilopascal. That's 101.32 kPa. So let's see if we can do some pressure conversions. So let's practice some conversions. All right, so if I have 562 millimeters of mercury, How many atmospheres is this? Well, this is a very simple problem. We'll take 562 millimeters mercury, and we multiply. Remember our railroad tracks. I'll say there's millimeters of mercury in 1 atmosphere, and that number is 760. Notice I get the millimeters of mercury to cancel, so I get my calculator. So I'm going to grab my trusty calculator, and I'm going to take 562 divided by 760, and I get 0.74 ATMs, rounded to 2 significant digits. Probably should keep 3, so that's actually 0.739 atmospheres. All right, let's see if we can do one other one. Let's say that I've got 56.3 kPa, kilopascals, and I want to convert that to atmospheres. I can then say kPa to ATMs, and that's that 10 ATM, not AM, 101.32 kilopascals to 1 ATM, and I can say 1 ATM is 760 millimeters of mercury. We often like to convert to millimeters of mercury, so here let me do that. 56.3 divided by 101.32 divided by, no, not divided by, times, hello, I can't do things here, times 760, and I get the round figure of 422. That would be millimeters of mercury. Now let me say one more thing about millimeters of mercury. 1 millimeters of mercury, 1, is also equal to 1 torr. Okay, now torr stands for a famous scientist, Mr. Torriellini from Italy, and he is the guy who invented the barometer, so, or Torricelli, it's Torricelli, and we just call it a torr. So Torricelli, so he's a millimeter of mercury, so I could just as well said this is 422 torr. Same thing, okay? All right. Now, that was the kinetic molecular theory of liquids. When we talk about gases, actually this is kind of a cool picture to kind of illustrate there. I have 3 states of matter here in my liquids. Here we have gas, and they're just kind of flying around, and they're separated. And right here we have the substance as a liquid. And the liquid, you see the molecules, they're kind of roving around and they're closely packed. And in the solid, all they're doing is they're doing the vibration thing. Okay, so they're vibrating. These are just flying around and are not attached. These are sort of loosely attached. And these are, of course, liquids. So this is a liquid, this is a gas, and this right here is a solid. Okay? All right, so what's up with the kinetic molecular theory of gas? So let's talk about evaporation. Evaporation is an interesting thing. What happens when something evaporates? I'll bet you realize this. Here we have a steam bath. This is a hot area. I think it's volcanic in nature. And what is evaporation? That is going from any state to a gas, but not boiling. So if you're taking a shower in the morning and it steams up your shower, then you're having it from a liquid to a gas, but it's not boiling hot. It might be hot, and you might think it's boiling hot, but it's not technically boiling. If you poured boiling water on yourself, that would be ouch. Way ouch. Okay, and so here is kind of a way to look at this. Here we have a microscopic equilibrium between gases and liquids. Note the rate of evaporation of the liquid is equal to the rate of the condensation of the gas. And so what we've got here is we've got the liquids evaporating right here. Do you see? This is a liquid down here, this bottom part, and you see only a few get enough energy. Think of it back to our Boltzmann diagram. I'm sure we call it the Boltzmann diagram, but this diagram of kinetic energy, where this is the kinetic energy, this is the kinetic energy, and this is the number of molecules. And you see these ones right here probably, who are the average, cannot escape. But the ones that escape are the ones that have the higher energy. And so that would be the ones. So they have enough energy to escape the liquid state. Interestingly enough, what I have here is a solid on this side of the picture. Now in this solid, sometimes even they also will have that same graph, right? This graph we're talking about. And just a few of them can escape. And this is the process called sublimation. When something turns from a solid to a gas. Okay, dry ice does this very well. Okay, in fact, well, here's a picture that kind of illustrates that. We can see which ones are going to escape. Maybe it's just these ones right here. And this would be, say, at 100 Kelvin, at 1,000 Kelvin. How many would actually escape there? Well, it'd be all of these, wouldn't it? Anybody above a particular amount. So let's say that only these above this line can escape. Well, if you are at 1,000 Kelvin, a lot of them will escape, almost all of them. And this one, very few on the blue line. All right. What about vaporization? Well, vaporization is liquid to a gas, but it can either be evaporation or boiling. I want you to kind of understand there's a difference between vaporization and evaporation and actually boiling. So either boiling or evaporation are both considered vaporization. All right. Now, what about vapor pressure? A new term. Lots of different sort of words to describe. What you should definitely do is draw some pictures as you do this, okay? All right. Vapor pressure is the pressure exerted by a liquid as it evaporates. So again, think of our pressure right here. These particles, as they evaporate, right, they hit so if the ball, ouch, hits me in the head, it exerts a pressure. All right. So if I have a sealed container, so think of this as like an aquarium right here, and we have water, right? And here we have the water, and some of it is evaporating. As these molecules move to the outside, they exert a pressure. They're hitting the outside. So they have a particular thing called the vapor pressure. All right. Some more definitions. All right. What do you think? The higher the temperature, about in terms of the vapor pressure, the blank the vapor pressure. What do you think? If it's going faster. Think. That's right. It will be higher. Yes, indeed, it'll be higher. Oh, I haven't even wrote it there. That's cool. All right. So a lot of definitions in this podcast, and this will kind of get us an understanding of how things work. Next time, we're going to talk about something, maybe the coolest demo of the year. We're going to talk about boiling. And I'm going to be able to boil some things. Boil. I will boil some things that are cold. Oh man, that's so cool. Okay, so that ends. I guess Mr. Sams could not pop in today because he is so busy with students. It's finals week actually, and I don't